And if you haven't seen the cartoon before, you'll understand it before today's lecture is over. So, jumping right in, the theme of the first part of the lecture is defending customer data. And I think I sort of said this last time, but it used to be that operations was sort of not at all your problem. You now have some operational responsibilities even as a developer, but really what concerns us here is what are the things that you have control over as a developer that will allow you to make good security decisions on behalf of your customers and their data. Because there are certain kinds of attacks like root shelling attacks and things like that, that if you're using platform as a service like Heroku, you don't really have direct control over that part of the infrastructure. So our focus, and by the way, we think that this is really increasingly the world is going. In fact, one topic that we won't have time to cover at all this semester, which is unfortunate, is the rise of so-called serverless computing, which I think is kind of a misnomer because clearly there's a server somewhere, right? But some people now call that FAS, for functions as a service. And there you have even less control over what your server environment looks like. So things are really evolving more and more towards where your role as a developer is going to be increasingly focused on not making things, not exposing weaknesses in your application. So these are not all, but probably some of the most common attacks on SaaS applications. All except the last one are generic to any SaaS framework. The last one about mass assignment is specific to Rails, and I'll talk about it in just a moment. But the first 5 are pretty much have been around since the beginning of SaaS. And as usual, we won't have time to cover all of them in lecture. The book has some more details on some of them, but we're going to talk about at least the ones that are in red, because those are some of the ones that are easiest to guard against and some of the most evil ones in terms of the damage that they can do. Mass assignment, just briefly, this was actually a problem in early versions of Rails where there was essentially a bug, well, not a bug, a misdesign, in which those beautiful forms where you can just like grab params entirely out of the forms and assign those params immediately to an active record model instance. Unfortunately, in the earlier implementations of Rails, that was done in such a way that you could potentially assign attributes that were sensitive, like the privilege level of a user or whether somebody has admin supervisor or something like that. And although you could disable that, the way that Rails used to ship is that that danger was sort of enabled by default. That has since been fixed, but if you want to read about it a little bit, that's in the book. So we'll focus on these other ones, especially starting with SSL, which is sort of the basis of web security. And there's a fair amount of, I think, misconceptions among less experienced programmers about what you can and cannot rely on SSL to do. The basic thing that it does is that it encrypts HTTP traffic between endpoints. So the one thing you know you can do is you can thwart eavesdroppers unless they've managed to mount an attack on the infrastructure, like a man in the middle. So the problem that SSL solved is that if you want to create a secure communication channel between any two entities, the basis of that channel is that the two entities know something that nobody else in the universe knows. So a password or an encryption key. And that piece of information is used as the basis of creating the channel securely. But on the web, the two parties don't know each other because you may be visiting the site for the first time. It doesn't know who you are. So something had to be done to allow the generation of some sort of a secret shared only by those two parties, even though the two parties had never had prior contact. And public key crypto solves that problem. It is a sufficiently cool thing that the 3 people whose names form the initials of RSA Data Security jointly shared the Turing Award for coming up with a practical implementation of it. So how public key crypto works is a little bit outside scope, but I'll give you sort of the schematic version. So what SSL does and doesn't do. Starting with basically just the basics of public key crypto. How does that work? In public key crypto, a key is actually 2 matched parts. They are generated at the same time. They correspond exclusively to each other. And the idea is that of those 2 matched parts, one of them is published for the entire world to know, and the other one is kept secret only to the person who generated it. So they're called the public part and the private part. And an important property is that given one of them, you cannot deduce the other. So they're uniquely matched. You can think of it as like a key and a lock, but either one can act as the key where the other one acts as the lock. And in particular, if you encrypt something with one half of that key pair, it can only be decrypted by the other half, and vice versa. So the use of this in communications on the internet is if you get your hands on a message and it turns out that the public part of Bob's key can be used to decrypt it, you can safely assume that the private part must have been used to do the encryption. And if Bob is a responsible individual, that Bob must have sent the message because presumably only he knows what the private key is. And conversely, if I use Bob's public key to create a message, then since only he is in possession of his private key, presumably, he's the only one who can read it. So that's, excuse me, that's the basis of what SSL does for websites. The idea is if you're bob.com and you're setting up a server, you first take a few steps to prove something about your identity to a certification authority. These are all over the place. And most of the time for sort of the baseline level of security, proving your identity is really minimal. Usually these days, all you're proving is that you control that domain, and that you have the ability to make changes to the way that the domain is configured. It's kind of like when a service asks for your email address or your phone number, and really all you're doing is proving that you have control over that email or phone number because you can receive messages at it. Once Bob has proven this to the satisfaction of the CA uses its private key, which ideally nobody in the universe knows besides that CA, to create a certificate that basically says this domain bob.com is in fact tied to this individual. It's tied to this website, which is registered to this company, et cetera, et cetera. Right? It's basically a pledge of good faith. And the operative phrase there is the private key of the CA is not known to anybody else. There have been major incidents in the news in the last 3 or 4 years where in some way or another, hackers were able to get access to the private key of some certification authority, which is really, really bad. Because then the hackers can create fake certificates saying that, oh no, actually my evil server is the one that corresponds to bob.com. And now browsers that are mistakenly directed there will believe that they're talking to the real bob.com server. The certificate gets installed on bob.com server. So the users of that server never have to really do anything because when their browsers visit the site, the public keys of the certification authority that signed the certificate are essentially built into the browser. So the browser has the ability to match that the certificate really was signed by a CA. The certificate really says that this website belongs to this company, and then all is good. And then those two pieces of information participate in something called the Diffie-Hellman key exchange. To oversimplify a little bit how it works, one of the keys is used to encrypt something, send it to the other side, which can decrypt it. That thing serves as a secret, and because it was never transmitted in the clear, nobody else knows it. So that's I'm oversimplifying a little bit, but that's the essence of how it works. And at that point, that can be used to secure the rest of the channel. So any further communication between the browser and bob.com are now encrypted, and eavesdroppers are in general foiled from being able to eavesdrop on the conversation. So that's the basic idea. Most SaaS frameworks have a pretty straightforward way to tell the app you should run as SSL. So, what part of this has to do with the app and what part of it has to do with the infrastructure? Well, it is certainly true that the infrastructure where your app is running, so, in your case, it's running on Heroku. Heroku's web front end, right, their HTTP servers have to have a way to do this entire process. They have to be able to negotiate SSL, which is what the process tends to be called. But there's also something that is incumbent on your app because HTTP and HTTPS are essentially different protocols. They both look the same. If you decrypt what's happening in HTTPS, it looks just like plain old HTTP, but they run on different ports. The way that the web server manages the connection is different. So as a developer, you actually have to make sure that your app knows that it is supposed to use SSL, because if a request arrives for HTTP something in your app, it does not automatically become HTTPS just because Heroku supports it. You have to do something, and in Rails, that thing is typically in your top-level application control, you say force SSL. And what that does, essentially, is anytime a URL is received by if it gets all the way to your app, like to some controller, and it looks like this, then the Rails stack will automatically issue a redirect to that same URL, but replacing this with HTTPS. By the way, that implies that you had better make sure that most of your URIs have RESTful behavior, because basically you're doing an immediate redirect and assuming that the result of the redirect is going to be the same as what the original URL was, right? So that's all you have to say. Good times. And typically, because it's a little bit painful to get for various complicated reasons, it's a little bit tricky to get SSL to work on your development machine. And the reason is essentially you have to create a certificate that vouches that your machine is the real local host. There's a way to do that. It's called creating a self-signed certificate, but most of the time you just don't need to worry about it. So a very typical thing is the force SSL call in the application controller will be conditioned on if the app is running in the production environment. If the app is running in the dev or testing environment, SSL will not be turned on. So if you've gotten this far with SSL and you now have a secure connection to the app has said force SSL. So from now on, any requests that come into the app are going to be forced, even if necessary through a redirect to be secure. What can you now assume about the app and what can you not assume? So it assures the browser that bob.com is legit, unless, of course, the certification authority that created the cert for bob.com has been compromised, in which case they might be running around creating fake certificates asserting that their evil server is bob.com. And this has happened a number of times. Really big sites like Amazon and Google have been affected by it. Because all the traffic is encrypted, eavesdroppers in general cannot read or in any meaningful way corrupt the traffic between the browser and bob.com. So there's data integrity on the channel as well as privacy. It creates some additional work for the server because all of that handshaking has to happen, the decryption has to happen. However, in the last 3 or 4 years, we've seen this trend toward SSL everywhere, where even non-sensitive or non-secure websites are moving to use SSL by default. So you can pretty much now assume that provisioning for platform as a service takes account of the additional work, and it's not really significant additional work anymore. However, you cannot do any of the following things. The server has no idea who the user is. All it knows is that there's some browser out there that is connected, and the connection back to the browser is now secure. The data going to the server is secure while in transit, but what happens to it after it reaches the server is anybody's guess. And as I'm sure you all know, if you read, about software in the news, the damage is done when the databases at the servers are compromised, right? The attacks are not generally done by attacking the connection. They're done by attacking the data at rest. So, for example, you might say a thing you could do at the server is you could store the data so that it is encrypted at rest. Therefore, if anybody got a hold of the database, they would still also need some separate decryption key to make sense of the data at all. And indeed, there are some Ruby gems that will do this. If you've got some particular data in your database that is unusually sensitive, you can automatically encrypt certain columns, and the encryption key only ever appears as a config variable in Heroku. So even if your entire database got slurped up by someone, those sensitive fields wouldn't be useful to them. They would look like garbage. There's a number of other attacks against the server, a couple of which we'll talk about in a moment, and SSL does nothing to mitigate them. So, and in particular, if the server is evil and it has managed to impersonate another server and it is intent on delivering malware to you, SSL doesn't help with that. You'll just receive the malware in a secure manner. So basically, the only thing you really get is data privacy and lack of tampering on the connection. And assuming the CA wasn't compromised, the browser and therefore the human being behind the browser can reasonably assume that the site is who it says it is. That when they visit google.com, the certificate vouches that this IP address, this server, this domain name, this really is Google and not somebody masquerading as Google. So it's actually not that much. So that's what you get from SSL. It's a good idea to turn it on. There's sort of no reason not to use it in production, but let's talk about some of the attacks that can happen on database-backed apps that this does nothing about. And the most popular is called SQL Injection, which is where the cartoon gets explained. This is a pretty standard attack that is so common and has been around for so long that I believe Code Climate even has special checks for it. And woe be unto you if you push code that allows for a SQL injection attack. So here's an example of how it works. In the view, there's a form that somebody is supposed to fill out with their name. Somewhere in the controller, that information gets used to populate a database statement, kind of like this one. And unfortunately, an evil person decides to fill in that phrase for their name. If you now substitute in that phrase, this is the query that you get, right? It does the original select, then it destroys the table, and the double dash assures that if there's anything after this part of the query, it becomes a comment, because double dash is the SQL comment character. And who has seen SQL injection before, or is familiar with the concept of it? Okay, cool. So, there's kind of a standard anecdote about, some evil school kid who did this. The solution is pretty straightforward. This is the reason that Active Record has this syntax, by the way. There are other reasons too, but if you use the official Active Record syntax for constructing your queries, it will do all of the necessary escaping to thwart this kind of attack. It's called preparing the statement. So basically, if you ever see something like that in your application code, that should be a red flag. I don't know if you guys have seen this, but for a long time, this is a meme that was going around. I don't know if this ever really happened, but the idea was that people were trying to foil traffic cameras by driving around with, the idea is the camera takes a picture of your license plate, and that's used to look up something in some database and then send you a traffic ticket. And that people were driving around with license plates that were, so I don't know if this actually works. It doesn't seem like to me that it would work, but I still think it's pretty funny. So I thought I'd put it in. Okay. So anyway, that's SQL injection. I think Code Climate checks for it, but this is like a basic thing, right? So please be careful when you're checking in your code. A little more fun than that is Crosssite request forgery. And this one is a little more subtle to guard against, but again, most good frameworks give you a straightforward mechanism. Here's how CSRF works. Some people call it CSRF. So Alice logs into her bank. That means, and Alice is a legit user. Her browser now has a cookie that is probably meaningful to that site. And in particular, the cookie probably contains whatever information when she returns to the site that the server will use that information to verify that she's logged in. Alice is accidentally redirected to some other site at, some evil website, or maybe she opens an email that is HTML formatted and came from that site. And either on the site or in the email, there's something like this. There's an image tag or a tag to fetch some other asset from Alice's bank, because essentially it's wagering that when that request goes through, Alice will already have a cookie that's valid because she's logged into that account. And at that point, the evil website might also try doing this as an AJAX request, which we'll talk about next week. And at that point, they're in a position to potentially harvest information that they would have needed a valid cookie to get, right? Information that is only accessible when Alice is actually logged in. So how do you mitigate this? There's a bunch of solutions. The weak one that people used to do is the HTTP headers have a field called referrer that shows where the most recent request came from. So if you are bank.com and the referrer field shows that the request is not coming from another page on bank.com, you have reason to be suspicious. But of course, that field can be forged, so that's not really reliable. There's a web scheme called cross-origin resource sharing that is designed to sort of manage permissions in exactly these cases. The idea behind CORS is that there actually are legitimate cases where having a third-party site be able to use a cookie that sort of doesn't belong to it might be a useful idea for things like developer sites and performance tracking and so on. But for the most part, most websites that don't fill kind of a developer role like that probably don't have a good reason to use CORS, which is kind of complex to get right. The easiest thing to do, which Rails does by default, is that every time you have a request to the site that is sensitive, certainly every time you have a post request, because those are the ones that can typically change state, the idea is that every request will include a nonce, which is a random string of characters that is used exactly one time. And the server can remember which is the most recent one it gave out. So for example, if my Rails app serves you a form where you're going to fill in some stuff, I will include, or Rails will include, as a hidden field in the form, this long random string. And Rails will remember that the last time it served the form to you, that was the random string. Now, when you submit the form, that random string comes back in the form of the hidden field, and Rails can match them up. If somebody else managed to get a hold of the form, and they didn't include that hidden field because it gets served differently to every party, just trying to submit the form, even with a valid cookie in hand, won't work, because the submit has to have a nonce, a one-time use token that matches the last one that Rails sent. And unless the person managed to get a copy of the form sent to them, it won't work. Even if they harvested the copy of the form that was sent to you and then tried to do a fake form submission using the hidden field, it still won't work, because once that form has been submitted one time, that one-time use token is used up. So this is a pretty reasonable, and by the way, the forms are already being served and posted over HTTPS. So intercepting the actual form content is tough to begin with if you have SSL turned on. So in general, this is a pretty effective way to thwart the most common CSRF attacks. And all you have to do is in your application top-level file, you put somewhere at the top of it CSRF meta tags, which are some tags that basically key off Rails to turn on this mechanism of including the hidden strings everywhere. And then somewhere in the top of your application controller, maybe right under force SSL, you say protect from forgery. That one line will basically make it so that every form served by the app will include this extra hidden token, and every form submission will include machinery to check that the token matches, and if not, it will raise an error and throw an exception, and badness won't happen. Okay, so I'm not going to talk about cross-site scripting attacks, which have a similar flavor but are a little more subtle to pull off. If you're interested in that sort of thing, you could do like an entire class on web security, but the book chapter is a reasonable start for some of those. To wrap up some of our discussion of DevOps, I think most of the projects that you would do at the level of a course like this over a semester, a lot of the stuff we've talked about really is not going to come to bite you in a first-class way, right? If your app is not being used by an enormous number of people, if the security perimeter around your app is already pretty tight, but these are the kinds of things that if you're using software that any significant number of users, end users, are going to use, you have to think about this stuff. So trying to summarize some of the themes, one of the pitfalls is basically premature optimization, by which I mean optimization without really knowing what it is that's causing the problem. If your app feels like it's slow, there's a million different ways that your app can be slow. And it's true that users want your app to be responsive, but you really first have to understand when the users say your app is slow, is it that it's always slow? Are there particular pages or actions that are slow and the rest of the time it's good? So using some sort of monitoring tools will give you some insight about that. And before you modify anything, measure and measure and measure, because you need to make sure that the things that you're trying to optimize are actually going to get you some bang for your buck. And we even saw a couple of examples of that when I showed my simple New Relic graphs on Tuesday, that the operations that take the longest time to do are not the same, in my case, as the operations in which the application spends most of its time, right? It turns out that there's a particular operation that is slow, but A, I can't control most of the slowness because it was involved in making a call out to another service. And B, even if I could control the slowness, that operation doesn't happen very frequently compared to other operations that happen all the time, even though they're not quite as slow. So in terms of where I'm going to put my effort, I'm going to put it on the place that is most frequently causing a slowdown for the most number of people. There's a whole bunch of great articles on New Relic's blog. Again, I have no financial incentive to plug New Relic. I just think it's pretty cool. But they have a nice set of articles about how monitoring of the kind that they provide can help you scale your app better and manage scaling more intelligently. And I think, to me, this is another example of, why do we use platform as a service? Because people who are professional database administrators, for example, are going to do a better job of optimizing Postgres than we ourselves are going to do. Why do we use something like New Relic? Because people who all they do for a living is think about what to measure in terms of performance, how to present that information, how to design alert mechanisms around it, they're probably going to come up with better answers for that than you would if you were just sort of ad hoc doing measurements in your app. So there's a lot of benchmarking you can do in your development environment as well, but there is no reason not to turn on basic monitoring of some kind if you're doing cloud computing apps. Fallacy. For a long time, when the idea that you could think of this app as a three-tier architecture where you have the web server tier, the app server, and the storage tier, and that sort of having these individual tiers manages or makes scalability magically work, of course we know that that's not true. Certainly it's not true of the database. Even if you have to scale the database, you need to deal with the expensive operations that might wreck your service level objective. So again, understanding from a monitoring perspective, what are the queries that you're doing? Are the queries the bottleneck? And if so, is it because you've accidentally missed something really basic? Like there's a query that really would benefit from an index and you just need to create that index. Or you've got a place where you have an n+1 query loop, and if you just optimized it away, then your performance would get suddenly better. So as I said, there's gems that help you detect both of those circumstances. And by the way, just to be clear, New Relic will tell you, for example, that this is one of the pages that takes the longest time to load. But it will not tell you the reason for that is you have a stupid n+1 query in there, right? You need a different level or a different kind of instrumentation to see that, which is why I suggested a couple of gems last time that you can just keep running in development, and they will tell you if you're creating queries that are sort of needlessly abusive. Besides that, you can deploy caching at various levels. Caching is what you do sort of as it's not your first line of defense, right? Your first line of defense is don't have a design that's abusive. Do all of the things that are reasonable to make sure that your queries are pretty streamlined, your page rendering is pretty streamlined. Once you've done the most you can with that, then you say, okay, where are the places where caching might be able to help? And for each one of those places, what is the most aggressive kind of caching I can do? You know, when can I cache an entire page as opposed to just caching fragments? And as I said, I think Rails support for how you talk about caching, which basically lets you change the caching policy in some sense without changing the models being cached or the views being cached, I think is a particularly nice separation of concerns. And if you do all of these things, it will have the effect of allowing you to stay in a nice managed environment for as long as you can. When I first moved over to Heroku, I had a bunch of apps that I had moved over, and I previously was paying something like $35 or $40 a month for a virtual private server. I administered everything myself. I had my own Postgres. I had my own SSL libraries. I did everything. And when I moved those apps to Heroku, my bill went to like $80 or $90 a month, which sounds like a lot of money, but the amount of time and grief that I have saved, the amount of additional insight I've gotten into where the performance problems are in my app because Heroku and New Relic work well together, that's more than worth it, right? So again, you're outsourcing and paying a little more, but you're probably going to get a better result than if you try to do those things yourself. So in case you can't tell, I'm a huge fan of everything having to do with platform as a service, because then I just have to think about my app, not about operations stuff that is really not a differentiating feature for me. From a security standpoint, do not assume, and I think I mentioned this earlier, that just because your site serves a very small audience, it's very specialized, there's no valuable data, therefore, why would anybody possibly attack it? They may be after personal information about your users. If you are smart, you will not keep any personal information about your users any more than you have to, like maybe just their email address. I assume, and if I'm wrong about this, I don't want to know, that none of you is actually doing something like collecting a credit card number and storing it somewhere. Besides the fact that that's actually highly illegal and can get you shut down and they can find the bejesus out of you, it is needless because you can outsource it to places like Stripe. There's the best practices and tools. I mean, really, these are things about the framework. So if, for example, somebody found a flaw in the Rails framework that would allow the cross-site request forgery to be gamed under certain circumstances, as a developer, it behooves you to stay aware that you rely on the framework to do some things. You should stay abreast of what is known about that framework. In fact, some of you may have noticed GitHub does this for you now. GitHub has gotten pretty good at detecting which languages or frameworks are used by your app, and it will cross-reference that to any recent CVEs, vulnerability notifications, that may be related to your app or framework. So if GitHub or Code Climate says there's a critical vulnerability in the framework you're using, upgrade now, you should take those things seriously. And of course, you're backing up your database. Again, on Heroku, this is one of those, check the box for how much money you're willing to pay. And that will tell you how frequently it's backed up and how old the oldest backup is. But you should just assume that at some point the database is going to be vaporized, whether it's because the app got compromised and somebody scribbled over the database or something else happened. So keep everything backed up, and if you're on platform as a service, that usually just means checking the right box and paying a little more money, and then turn around and charge your customer for that. I think for me, the takeaway is when we're talking about performance and security, even though we're only talking about things in the app and not so much things in the infrastructure, all of the abstractions become leaky when performance and security come into play. So we looked at external monitoring. It tells you the uptime of your app. Internal monitoring that can help you pinpoint performance problems. But caching, right? Caching is basically admitting that the abstraction of this ultra-fast database and view rendering is a myth. That sometimes you have to get in there as a developer and say, all right, these particular actions would benefit from being optimized, and now I have to worry about the circumstances under which I have to invalidate the cache, et cetera, et cetera. That is a leaky abstraction, right? All of a sudden, you have to come into closer contact with the implementation of the thing, and rather than just sort of thinking at the level of how it's designed. Same thing for database tools. Places where you have n+1 query problems or where you are lacking an index that would have been really helpful, those are, that is an admission that the relational model for storing these objects, the graph of objects like active record models, that is a leaky abstraction. That there are ways that when you construct those queries could have a first order impact on performance. And again, you have to know something about the way queries are implemented, the fact that doing a has many means you're doing a table join, and eagerly loading the second table is going to save you from doing n+1 queries. You have to just know that, right? And that's a big step down from just pretending that we say has many and then we're done and everything just works. From a correctness point of view, everything does just work, but once you start worrying about performance, it's not that simple anymore. So I think part of the judgment of a good software engineer is understanding what are the limits of the abstractions you're using. Where do those abstractions break down, or where do you have to be careful about things like performance and security, and make sure that your design essentially accounts for those in a reasonable way. And finally, when anything's wrong, you have to measure before you fix. Web apps have gotten extremely complicated, and that's even before talking about all the additional stuff you have to worry about when you do JavaScript, which we're going to start in just a minute here. But whatever the problem is, do a lot of measuring first, and measure before you try to fix anything, or you'll never actually know if it worked.